Welcome, everyone. Today's session, we took a break. We didn't have a seminar 2 weeks ago, but we continue on our focus topic, which has been galactic cosmic rays, measurements, and theory. And today, we are very pleased to have Dr. Giada Peron from INAF, Italy, and she's going to talk to us about pion bump detection and hadronic component of gamma rays. So I hope the title is okay for you, Giada. So Giada, as you know, is an expert on probing the spatial and spectral distribution of galactic cosmic rays with high energy gamma rays. She's currently now a fellow at INAF Arcetri, and she's investigating the role of stellar clusters for galactic cosmic rays. And she has previously held postdoctoral research positions at the EPC in Paris with Stefano Cabici, MPIK Heidelberg with Felix Aharonian and Jim Hinton, after having received her PhD working with Professor Felix Aharonian. And some of her recent work, I think you may have seen some very interesting papers from her recent times. There was one on the cosmic rays from future MEV detectors, hadronic acceleration, young star clusters, unveiled by Fermi, interpreting the LASSO diffuse emission data, among others. So there's a lot of interesting work that she's done. And recently, she has been a member of CTAO as well as AS3, and she's presently the working group coordinator at AS3. And some of the highlights, she won the L'Oreal UNESCO Prize in 2024, the Binyami Prize in 2025, and she recently gave an invited highlight talk at the 39th ICRC on star clusters in the gamma ray sky. So it's a great pleasure to welcome Giada, and thank you again for giving this talk. I'm going to mute, and I'm going to ask everyone to mute. Do you prefer questions during the talk or at the end, as you like?
I have no preference. I mean, if you feel like interrupting me, I should.
Yes. So just speak up.
I don't mind. Yes,
Okay.
exactly. I
And
should
just
be
a reminder that we will be recording this for our YouTube archives, and I hope you continue to join these seminars. So thank you very much for coming, and Giada, please get started.
Thank you, Rashmi, for your kind words. Actually, I'm the one that should be thanking you because it's a real honor to be presenting to this crowd. Where I was thinking today that usually the crowd that participate in these seminars are the authors I read to learn something. So it's really a challenge for me to tell something that will be new for someone. So I hope I'm not too boring for you. I hope that I can stimulate some discussion about this topic and give some new ideas in this context. I'm glad that you commented on the title because it was a bit challenging as well, this title for me. At the beginning, at least, it seemed a bit weird. But on the other hand, I realized that indeed the hadronic component of gamma rays and one of its most intriguing feature, which is the pion bump, are really interesting because, as you said, I'm one that in my research, I'm interested in understanding the cosmic rays and the galactic cosmic rays. So, and this is tightly related to the hadronic component of gamma rays. So in the end, I found out that I didn't know I was studying the hadronic component of gamma rays, but in the end I do. So let me walk through my talk. So I am starting with a question. So why are we interested in hadronic emission? Actually, this is a question I recently received from someone out of our field, which is kind of my starting point of my talk and relates to the physics of cosmic rays. I think you all know that when we look at the cosmic ray spectrum, at the composition of the cosmic ray spectrum, we know the elements that compose the cosmic ray spectrum. We know that we have protons, we have helium nuclei, we have heavy nuclei. And we know that what is the most numerous component of cosmic rays are actually hadrons. So when we wanted to explain what are the cosmic rays and what is the origin of cosmic rays, we need to take into account hadrons because leptons are also an important component, but they are in general subdominant. And you see that what we measure, the ratio between the cosmic ray electron and cosmic ray protons is actually energy dependent. We have now measurement that goes also below GeV thanks to Voyager. But at high energies, we see what I was saying, that the ratio between electrons and protons is to the order of 1%. So and this is also telling us something about what are the sources of cosmic rays. So, well, actually, how can we connect the cosmic rays that we observe at Earth to the electron to protons that we see at sources? If we do a really simple back of the envelope calculation, you see that if you assume a very simple equation, when you assume that all the cosmic rays that we observe are the same, that have been produced, but they just propagated or they lost energies, you find out that what is the relation between the electrons of protons that are produced are related to the electron to proton ratio that we see at the Earth modulated by the typical time that dominates proton losses, which is only escape, and the typical time that characterizes electron losses, which could be either energy losses or the escape time, which is the same for electrons and protons in first approximation. So if we study this ratio, we see that more or less the injection of electrons should be of the same order of electrons and of the ratio that we see at the Earth. But if we go and have a deeper look in what is the physics behind this, you would see that by taking into account average galactic magnetic fields like the CMB, the infrared, the ultraviolet, and infrared and average magnetic field, and you take into account a standard diffusion model in the galaxy, you see, and you can evaluate easily what are the lost time of electrons, and you can evaluate what are the escape time of electrons and protons. And what is interesting for me that emerged is that even accounting for the different lost time and the different propagation at the different energy, the dependence of the injected electron over proton ratio is somehow energy dependent, which is something a bit interesting to take into account, because it relates directly on what is the acceleration that we have at sources. So if we see the amount of the different spectral energy distribution that we have is of the order of the slope difference is of the order 0.3. And since it's a bit weird to assume that electrons and protons are accelerated in different ways in galactic cosmic ray sources, we have maybe to take into account that is written in a bit in a strange mode here, but there was an idea by Morlino and Celli that published in 2021 that maybe the ratio between electrons and protons that are accelerated in supernova remnant, actually, well, in supernova remnant, but actually in general in shocks, may depend on the velocity of the shocks. But since in supernova remnant the velocity of the shock after the first phase decreases with time, this may mean that the ratio increase in time. And since that the maximum energy also decreases in time because it decreases with the velocity, this may mean that electrons are better accelerated or more efficiently accelerated actually when the velocity is smaller, so when the energy is smaller. And this may create an accumulation of low energy electrons that makes the spectrum steeper. And this is an interesting result, but yet that needs some observational support. So, in general, as an introduction, we can conclude that hadrons in general, they will tell about the origin of cosmic rays. This because if, for example, supernova remnants, that we all consider the main contributor of cosmic rays at the Earth, if they are really the main contributors, they must not only accelerate protons, but they also must accelerate more protons than electrons. In general, since we know that at the Earth, electrons are contributed also by other sources that accelerate also mostly leptonic particles, we know that the fraction that we measure at supernova remnant must not be, it should not overcome much the ratio that we see at the Earth. So it should be actually be smaller than this, or actually comparable. And also this tells us that if we want also to probe other type of accelerators in our galaxy, and now we have different accelerators, they should respect a similar ratio between accelerating electrons and accelerating protons. So in general, if we have to remember that the main contributors of cosmic rays at the Earth, they must produce hadrons and in a large fraction, so mostly hadrons than electrons. And to prove that, we want to search for hadronic signatures in their gamma ray emission. So this brings me to the question, how do we recognize the hadronic emission at sources or in general? To understand that, we can revise what are the basic of hadronic accelerations. We know that they are produced by interaction of nuclei or with ambient nuclei or ambient photons, producing pions and either neutral pion or charged pion, then decay in gamma rays or in muons and neutrinos. So the main characteristics of the hadronic interaction is that the process has a natural threshold because the interaction need to produce pions. So we have at least the threshold that is given by the pion mass. And the process has also to produce neutrinos. So in general, if we have neutrinos, we are pretty sure that we are observing a hadronic interaction. Other than that, there are other external signatures that characterize hadronic emission because the process needs a target. And the target can be high density gas that provides nuclei for proton interaction or proton nuclei interaction, or a high radiation density, for example, in the pi gamma interaction. But also, we can also use to recognize hadronic emission, we can use the observation that comes from multi-wavelength, because we know that in certain energy ranges, for example, in radio and X-rays, there will be the leptonic component of cosmic rays producing emission through mainly through synchrotron, and this can help us, and we will see some example, can help us in constraining what is the leptonic component also at higher energies, and so to isolate the hadronic component at the energies that are relevant for our studies. So to revise a little bit, what is the threshold for pion production? Well, actually, I wrote a pion, but nothing, sorry. And I redid this calculation that I will leave you to check on your own. You will have the slides and find all my mistakes. But just to say that the threshold to produce to produce gamma rays via proton-proton interaction is around 300 MeV, which is actually the energy range probed by Fermi-LAT or instruments like Agile. And instead, for producing pi zero via the P gamma channel, we have a much higher energy threshold that, however, depends on the field of the radiation field of the photons that are onto which the protons are interacting. So you see that the threshold is quite high, but if we have a high UV field or a high X-ray field, we can fall in the range of particles that are probed by LASO. Of course, this is the energy of protons, so when you have to convert in the energy of gamma rays, of subsequent gamma rays, but still it's interesting because it will fall in the energy range of LASO. And I'm sure you have seen one of the most recent example, if not only, if I'm not mistaken, is the very interesting case of the Cygnus X3, which shows actually a bump that is called a bump in the paper, which was presented by the LASO collaboration, I think, a few months ago. And you see that you have a peak that goes above hundreds of TeV, actually above a few hundred of TeV, which is much consistent, very much consistent with the expectation that we have for production of photons via P gamma interaction. And it's very interesting because in the region of Cygnus X3, since it is a microquasar, which is a binary system in orbit with a Wolf-Rayet star, the emission, the radiation field of UV and X-rays is quite high. So the model is well consistent with the observation, and this might be one of the one of the only proof of this type of interaction. But this will mean that the protons have a very high energy. So in this sense, here I wrote that they are ultra energy protons because they actually are in the PV range to explain this. Okay, so this was the bump that was revealed by LASO and is expected because of the threshold in the P gamma interaction. But let's go back to what is actually the real pion bump, that is the one at low energy. So the pion bump is a really interesting feature because it's quite natural, and it just depends on the process, on the decay of the neutral pion. So I went back and revised the theory behind that, and you see that what is interesting that is to take into account is that what creates the pion bump is the fact that the pion decays into two photons. The two photons, they do not have a preferential direction, and so they are produced isotropically. They are produced with no preference direction. And they take both an energy that is half of the mass of the pion. So what creates a distribution of photon energy in the end is only the distribution of pions that here I called gamma, taking that is the Lorentz factor. So if you transform back in the lab frame, so in the pion rest frame, it will see two photons going in opposite direction with the same energy. But in the lab frame, you simply do a Lorentz transformation of considering the gamma factor of the pion, and you find that the distribution of photons has this shape. This shape, it depends on the cosine of the angle of the direction of the pions with respect of the lab frame. That means that we have a minimum and a maximum energy of electrons. But since there is no real preference in the direction, since it is isotropical, the distribution of a photon, which is the distribution of photons, which is emitted from a pion which is of the same energy, a pi, it must be constant. So for a single pion, we have a constant distribution of probability of being produced. And if you work out the math, you see that this distribution is not only flat, but is also symmetric around the half mass of the pi zero. This means that if you have, this is for one pion, so if you have pions with different energies, you will change the extreme of the minimum and the maximum, and you will change the normalization, but in the end, the mean value does not depend on E pi. So in the end, you will have accumulation of photons around the half mass of the pion. This, if you work out the math, also considering not only so if you this is for different pion energies. If you work out the math considering a power law distribution of pions, you find that the minimum and the distribution will be dependent on the minimum energy of pions, so the minimum energy of the extreme here of the integral. And you see, so far so good with this is only math, but in the end, if you write the minimum energy, so the lower bounds of the integral as a function of the photon energy, you actually find an interesting shape, which is the one written here, and you see that the distribution which I plotted here is the same solution here that I also reported here. So the cumulation of the integral emission of a distribution of pions which are distributed as a power law, you will see it will be with this symmetric shape, which is centered again in the half mass of the pion, which is around 768 MeV. And it's very interesting in the dn over d distribution. And if you multiply by E squared, you will see that you somehow have a peak a bit above the pion, the half pion mass. But so in the end, we expect in the gamma rays to see a rise and a decrease, which depends, well, if you multiply by E squared, it depends on the spectral shape, on the spectral, how do you call it, the spectral index. But in general, you expect the distribution to peak at this energy. So this is very interesting because this is actually the range probing by Fermi-Lat. Unfortunately, Fermi-Lat observed down to 60 MeV. 60 MeV that can be probed really for very, very bright sources. But if we will have in the future instruments like Amigo X or New Astrogram, which they are being proposed as MEV instrument, we will be really able to probe this part of the spectrum, and hence to probe actually and recognize this feature in galactic sources or in general in sources. And you see here, this is the sensitivity curves of the Fermi-Lat and on the prospect for New Astrogram and Amigo X. This is, of course, the normalization of the curves here are random, but you see that the energy range to probe the pion bump with Fermi-Lat is where in the Fermi-Lat is at the edge of its capability. With Astrogram and Amigo, we will be at the best of their capability, and therefore it will be very interesting to probe this contribution. I think I'm very slow because, but I will continue. So in general, but with Fermi-Lat, with Fermi-Lat and Agile, actually, we had a few detection of this pion bump. And one interesting, the interesting example that comes to mind to everyone is the W44 and IC433, which are middle-age supernova remnants. And you see that the shape it's really remembering what we see before in the calculation, in the theoretical calculation, where you have a peak at the right energy and the real shape. But at a certain point, people started to wonder whether you can also reproduce the spectrum, not only with the Pio-0, with the Pion bump, but also with a Bremsstrahlung. Bremsstrahlung with the break, if you assume that there is a break in the spectrum of electrons, is possible also to explain. I'm showing this here. You see that you can reproduce the Pion bump, but also the spectrum of using a Bremsstrahlung. But a characteristic is that if you put a low energy break, then the spectrum of Bremsstrahlung will be at the hardest that you can do is to have 1 over E, because it's the spectrum when the distribution is really cutting off. It's the spectrum of single particle, basically. And so you see that if you could go to lower energies, you will be able to distinguish these two features, because the Pion bump goes down much in a steeper way. So if we don't have enough sensibility with Fermi, it would be interesting, and if we had an MEV detector, to recognize the two components actually at slightly lower energies. It will be sufficient to recognize the two features. Unfortunately, as I think you know, there is actually a very big gap in the MEV band, which hopefully will be filled soon, but at the moment we stand to this point. Another interesting thing that we could do having an MEV detector is actually to probe what is the ratio at the sources. So assuming that this is actually produced by the Pion bump and this is the hadronic contribution, we could also prove what is actually the ratio of electrons over protons. This is much more interesting than what you can do with other type of in other type of energy ranges, because at this here is where the Bremsstrahlung dominates, and the Bremsstrahlung depends on the same way, depends only on the density of the medium, just like the protons. Therefore, the normalization between the two components is really directly related only to the KEP. And so it will be very interesting to prove, we will have possibilities to prove this type of emission and the ratio of electrons over protons. And not only, well, I was showing the example of W44, but we have already a few examples of sources where we can make some estimate that just taken by the supernova remnant measured in the Fermi-Lat catalog. So we will be able to test a few sources if we had some instrument, of course. Okay, so in the end, the Pion bump will be very interesting to measure the hadronic component and to evaluate what is the contribution of hadrons, but we have to deal with the fact that the Pion bump may not be there and we may also not be able to recognize it all the time. Actually, I asked ChatGPT to say, where is the Pion bump being recognized? And I was thinking only in IC433 and W44, and it confirmed, as always, ChatGPT confirms always what you want to hear, so you have some confirmation. Other supernova remnants, they do not have a spectrum like W44 or IC433, but you can see here a compilation made by Marianne Lemoine-Goumard at the last ICRC. You see that most of supernova remnants, they have a hard spectrum. Many that we see, they have a hard spectrum. And she concluded in her discussion, if I'm not wrong, that since they have a hard spectrum and a similar age, a similar environment, it means that they are accelerating particles with a similar efficiency, and the fact that they have a similar spectrum, but not only spectrum, but also the same luminosity when normalized to their distance, is telling that basically we are probably seeing something which is interacting with a field that is constant over space, which could very well be the interaction of electrons with the CMB. So in conclusion, it may seem that this type of supernova remnants are actually dominated by leptonic emission, and so the hadron components, if it's either is not there or we cannot measure. But you may wonder if this type of spectrum is the only possibility. So there is one case at least that has been for long time debated, which is the case of the supernova remnant, the young supernova remnant J1713, which for several years was discussed because it seems that a leptonic model doesn't work very well, and the hadronic model seems to work under certain conditions. Why is that? You will see that if I see a spectrum like this, very hard and with a cutoff, I would say this is inverse Compton, and that's it. But it appears that it can be explained also with other type of interaction, and especially also with hadronic interaction. Let me skip for 1 second this because I'm very, very slow and I see the time is already going. But I want just to mention that you see that there has been some proposals that this hard spectrum could also be explained. Is not a conclusion for a leptonic model if we take into account the propagation and the interaction of hadrons with clumps of gas. The thing is that to penetrate clumps of very dense gas, you need some times. So the longer for low energy and it is an energy dependent effect. So low energy cosmic rays may be suppressed and hence do not interact with the gas, so they produce less emission, so less hadronic emission, because they are not able to penetrate very dense clumps of gas. The calculation that has been done by Silvia Celli with Stefano and Felix, actually they proved that it's possible to reproduce the spectrum of 1713 only by taking into account clumps of that protons may have problems to penetrate. So since I tend not to believe to theories, even if they are beautiful, we have to have observational proofs. So in gamma rays, we will have if the clump scenario is actually true, we will have some spatial fluctuations. Of course, we will not be able to resolve the clumps alone unless we go to resolution of arc seconds, but that's not in the foreseen future. But also we will have the production of neutrinos because, as I told you, the hadronic interaction produces neutrinos. Anyway, even smoothing to the CTA resolution, we will have a different prediction for CTA that could see given the distribution of clumps. But also we will have, it's interesting to see that the instrument for neutrino detection like the KM3net will be able to prove the emission of this type of supernova remnant. So actually tell us the truth about the distribution of particles in this remnant. Okay, then another, so as say here, it will be hard to see, it will be interesting to see the correlation with the clumps of gas, but it's very difficult because they are very small, they are expected to be very small. But in general, if we see correlation of gas and gamma rays, we tend to conclude that it is of hadronic origin. I'll show you some example here. One that is very interesting is the supernova remnant W28, where you see that the correlation with the gas is very one-to-one. You see where there is the here you see the Hess contours overlaid with the map of gas traced by an antenna. And you see where you have the peak of gas, you have also the peak of Hess emission. This is interesting because it's tracing particles that has been accelerated in the remnant, but they started to escape and populate the surrounding medium. So not only we are able to prove that they are accelerator of hadrons, but we are also able to prove what is the past power of acceleration of this type of sources. It seems convoluted, but it's only because, as I was mentioning, for supernova remnants, the energy, the maximum energy decreases with time. So if they had the high energy particles, they may not be produced at the remnant at this time, but they may have been produced in the past and now are being in the surrounding of the remnants. So testing also the hadronic emission in the surroundings of sources is interesting to prove what was the acceleration power in the past. And this brings me to, I could not ignore this paper that was presented 2 days ago on the archive from the LASO collaboration, where they see and they present an analysis of 2 supernova remnants where they see emission which correlates with the gas. And as I was saying, they have the energy spectrum that extend much further than the spectrum of the remnant itself. And therefore, you see what could be, if is really proven to be correlated with the remnants, it can be actually the first proof that we are seeing very high energy emission from supernova remnant that are not accelerating this anymore, but they have been doing this in the past. So I think this is very, very interesting. So I talked a lot about supernova remnants, but there are also other type of sources where we see actually the correlation with the gas. And one very recent example is this cluster, NGC 6611, which is a very young massive star cluster. Is actually around 1 mega year old, which is quite young for this type of systems. And you see that from this map you can understand that we see extended Fermi-Lat emission in the circle here, and we see a gas cloud here traced by the contours, the white contours, and you see that the emission is not coming from the center of the cluster, but is coming from the region of hot gas, of dense gas. This is not unexpected, because we know that in this type of systems, the stars, the powerful winds that powers the star, they blow a cavity in their surroundings, which you can maybe imagine here, where there is this hot cavity. And but at the edge of this bubble, of this cavity, the material is swept up and form a shell. And here is where there is the dense gas, and is where our cosmic rays are produced inside the cluster, interacts, and then emit in gamma rays. And seeing this emission allowed us not only to prove that this type of source accelerate cosmic rays, but also to estimate the efficiency in the efficiency of accelerations, which we evaluated to be of order of 1 to 4% of the luminosity of the winds of the stars. But this is not the only case, probably in the galaxy, because another result that we obtained was to see that this type of sources, which are often traced by H2 regions, they are actually a phase of stellar clusters, which are actually naturally connected with the dense gas because they form out of dense region of gas, and for a quite large fraction of their life, they spend it in a phase which is called embedded, where they have dense gas in the surrounding of stars. So for us, stellar clusters are ideal places where to test hadronic acceleration and interactions. And it's very interesting to see that there is a very high degree of correlation between unidentified sources from the Fermi-Lat catalog and H2 regions, because H2 regions are tracing embedded star clusters. Therefore, we see that when we can explain that a part of sources that are in the Fermi range may actually be related to a similar effect that we've seen in the previous clusters, therefore acceleration inside stars, which is illuminating and interacting the surrounding gas. So the fact that also that is very compact around the stars allows us to really connect and find a nice correlation, because basically the emission is basically co-spatial with the cluster. So because we have just the target at the right position. Of course, there are also exceptions to all these nice pictures, where we have that one of the only supernova remnant, one of the only sources where we see the Pion bump, actually has also emission which is found in the surroundings. You see here there is emission detected by Fermi-Lat at the edges of the shell of the remnant. But if you go and study the gas in the surroundings, you see that these regions, they do not correlate with the position of densest gas. And this is a conundrum that could easily be explained if you consider the measured magnetic field in the remnant, and you see that these are the lines that represent the direction of the magnetic field, and you see that more or less they are actually oriented along the main axis of the remnant. This explains also the elongation of the remnant along this direction, but may also play a role in driving particles to illuminate this part of the gas and this part of the interstellar medium, and actually ignoring completely dense regions of gas which are in the surroundings. So gas correlation, yes, but also we have also to mediate with propagation and injection into the interstellar medium. I here wanted to make some consideration also from sources to the diffuse emission. I've seen that we will have a dedicated seminar next week, so maybe I will be quick about that. But I just wanted to say that also from the diffuse emission, we can actually probe the hadronic component of gamma rays and the hadronic component of cosmic rays. I'm sure you know that what we see in gamma rays is the interaction of protons that left their accelerators, and they are propagating and interacting with the interstellar medium in the galaxy, in the galactic plane. But when we look, at the emission and we try to understand what are the components, we know that in the galaxies, we not only have the pi zero, so the hadronic components, but we have a very hard superposition, a very a numerous superposition of components. We have sources, we have the inverse Compton component, we have all a sort of contaminating sources. Therefore, the analysis is quite complicated, but still we can get some information from this. For example, we see what is one of the questions that come into mind is to compare the hadronic component seen in the diffuse emission with the hadronic component of cosmic rays at Earth. So if you see the expectations, they are, this is discussed very well in the paper by Elena Orlando. You see the expectations that we have based on the cosmic ray spectrum measured at Earth do not very well match with the measurements that we have from the diffuse emission. Maybe this is a problem of analysis and so on, but still it's something which is indicative. Problem of the analysis meaning that they have many there are many components that superimpose, so it's very hard to disentangle, but still we should be able to do it, and it seems that it's quite different from the expectation. And if you try a best fit, you will see also that you lose at low energies. So there is not really a way. So it seems that the diffuse emission is somehow enhanced compared to the expectation. And when you go, and this is only for the local medium, because we know that in the galaxy, when you go to the inner part of the galaxies, maybe you cannot read here, is written the galactic center radius. The more you go towards the center of the galaxies, the higher normalizations you find of your gamma ray emission. That would mean that you have a higher value also of cosmic rays with respect to what measured at Earth. When you go at higher energies, it's even more complicated. We now have a few measurements from LASO, from HAWK, and from Tibet, which can be compared also to the expectation based on the local spectrum. You see that the situation is a bit interesting, is a bit different, because you see that in some cases it seems that we fall more or less in what is our range of uncertainties, but in some cases is instead enhanced compared to the expectation. There is a big difference between the data points measured by LASO and the one measured by HAWK, is that in the LASO analysis, they actually exclude some regions by applying some masks to derive the diffuse emission. So to do that, so when you do that, and you see here the representation of the LASO mask on the galactic plane, and actually you are acting by excluding the central part of the galactic plane, because here in projection is where you have the most of the gas in the center of the galaxy. So if we look at LASO, we see that when masked, it's compatible with the local expectation within uncertainties. We are somehow happy, let's say. With HAWK, you see that having no masks, you can expect to have a contribution also from sources that are in the inner galaxy, or it could be that actually is the same discrepancy that Fermi-Lat see, so maybe it could be a spatial-dependent cosmic ray density. But when we also look at the Fermi emission here, you see it cannot. When actually this is a new analysis, is not the one that was presented before, is one that should have the same mask as LASO. So this enhancement is hard to explain with a spatial-dependent cosmic ray in the inner part, because the inner part is actually masked here. So one solution could be unresolved large-scale unresolved sources, which actually come out of these masks, and they extend over the galactic plane, but the solution is still not there, and the question is open. I wanted also to say that with the molecular clouds, when looking at smaller regions, you can actually have less contamination from other source components, and you have you are less affected by fluctuation of the cosmic ray spectrum. And if you compare it to the measurement of the diffuse emission, you see that with clouds, we are actually able to reproduce the cosmic ray spectrum directly measured at Earth in many locations of the galaxies. Still, we find fluctuations which are fine because the cosmic rays, they do not stay still. There are sources, there are a lot of things that could happen, but in a few cases, we can actually recover the cosmic ray spectrum at Earth. I think I will skip this part. I'm sorry about that. But I don't know, like Reshmi, what do you think? Should I hurry up? I've been talking for 50 minutes, I think.
It's up to you. You know, you can finish up. I mean, you have a little bit more time, so certainly. I think some people have to leave at the hour, but we do keep on talking for the next 30 minutes beyond that.
Okay, okay. Then I will relax a bit. Okay, I think I had to be more sharp. Okay. So another thing that we have to take into account is that we have also now measurements of the diffuse neutrino flux from the galactic plane. And this is actually a smoking gun of hadronic sources in the galaxies because they are the only one that can produce neutrinos. And an interesting studies has been done is actually to constrain what is the fraction of sources that are hadronic in our plane, in our sky. So if you consider here that this region is excluded because it's what you get from known sources, from leptonic and hadronic sources. So if all this would be the flux if all sources are hadronic and they have no cutoff. You see that actually in our galaxy, the fraction of hadronic sources is around 40% in a model that allows particle to go up to 500 TeV, and must be much smaller if you consider a cutoff at 5 PV. This is something which does not conclude on the origin of sources and of hadronic cosmic rays, but still it's an indication of what we can do, how many sources we can have within our galaxies. So they are there, but they must have some constraints set by the recent neutrino measurements. What could be then the sources of neutrinos that are contributing to the diffuse emission? Of course, here diffuse emission means all type of sources and all type in the entire galactic plane. If we sum the neutrino emission expected by the diffuse gamma rays, meaning the propagated cosmic rays, and we do some population studies of supernova remnants and star clusters, you see that what we thought they could be hadronic emitters, as I was saying, because we see in a few cases, you see that they may have a significant contribution. This is a preliminary work by Stefano Menchiari, of course, being a theoretical work, it has a few assumptions, but still within reasonable assumption, we see that the contribution of star clusters and supernova remnant may be significant to contribute to the neutrino diffuse without violating what we measure in gamma rays. Okay, so this is to say that we now are starting to see neutrinos, and we are starting to have real proofs of hadronic accelerations from neutrinos. But before reaching to the real to a real multi-messenger domain, where we will have the measurements of neutrino emission from sources, we can rely on what we have already, that is the multi-wavelength data. So you know that non-thermal sources like supernova remnant, they are often emitting also in X-rays or in radio. And this is very useful to model the emission and to isolate the hadronic component with respect to the leptonic component. Here I show you an example. So since supernova remnant are bright in radio due to their synchrotron emission, and actually also in X-rays, you can see that you can put constraints on the leptonic fraction, which is from these two wave bands. So you can fit the synchrotron and derive limits on what is the high energy part of leptonic emission. So since we put some higher limit on the leptonic emission, we are able to isolate the hadronic component. And this is nice. This is an example for the case of Tycho, but it has been done also for other supernova remnants and allow us not only to prove the hadronic nature, but also to evaluate what is the fraction I started from of electrons over protons. For example, for Tycho, the authors Giovanni and Damiano derived that a factor around 10 to the minus 3 is very well suited to explain all the multi-wavelength data. We see that there is a collection of results that has been collecting over the years. I realized we should maybe put them all together in a clear way, but you see that in general there is a tendency of having a young supernova remnant with a smaller KEP and a somewhat bigger KEP when we go to middle-age supernova remnant. And this would be very, would suit the scenario where I told you that KEP decreases with the velocity, increases with the velocity, because in supernova remnant shock, the velocity decreases with time. So in this scenario, we have something which goes, I'm not saying it's a proof, but goes into this direction. Okay, but again, this is not only possible, not only with supernova remnant, because we also have some measurements of non-thermal emission from radio to X-rays, also from our embedded star clusters. I'm showing you now some results that I'm working now, I'm working on right now, and which are on the embedded star cluster RCW38, which is also a very young star cluster, also embedded in a very dense medium. And you see we have emission that spans from a few megahertz to GeV emission here, up to 100 of GeV. So what we see here is that the spectrum is quite different with respect to what we see, for example, in supernova remnants, for example, in Tycho, where you see the synchrotron here, which is dominating. Actually, the emission here is dominated by the infrared because the cluster is embedded in a very dense medium, and so the dust is emitting in infrared. The dust is heated by the gas, by the cluster, and emitting thermal emission in the infrared. You see that we have a nice correlation between the Fermi-Lat contours, which are here in white, and the infrared emission, which is here in gray. This is also expected when you have that the gamma ray emission is hadronic, so it interacts with the gas, and the infrared emission is thermal, so it is correlated with the dust that is emitting its thermal peak. So we fit this model, and we see that again. I was anticipating. We have a very high component of thermal dust. We have free emission, which is something that is naturally expected in this type of sources where you have hot gas. And there is also, actually in the radio component, we do not see the synchrotron, but we can put a very strong constraint on its normalization. So the normalization here put also constraints on the Bremsstrahlung and on the inverse Compton emission, and therefore in the high energy part we see that the dominant component that emerge is again the pion decay emission component. We derive some limits on K and P, considering that it cannot overcome the synchrotron cannot overcome the measurement here of in the radio band, and we see that it's also on the order of 10 to the minus 3. It is not. It is how do you say is. It is correlated to the magnetic field that we also fit together, but having some limits on the magnetic fields and on the by other constraints, we see that is of this order of magnitude, and so we see that is on the KAP, which we derive is of the same order of the one we derive for young supernova remnants. So if we put here the comparison of supernova remnants and RCW38, you see that it has values which are very nicely comparable with the values that we find with the supernova remnant. Which is interesting because if you remember my premises, we know that what should be if a source class has to be promoted to contributors to cosmic rays, they must accelerate more hadrons than leptons. Of course, this is a paper under preparation, but still I think it is an interesting hint towards this direction. And with this, I finished the things I wanted to tell you. I stress you again that we are seeking for hadronic sources because to explain the cosmic ray spectrum at Earth, which that foreseeing the pion bump that was the topic of my talk, we need different type of instruments because we need MEV instruments that really probe that area of the spectrum. And anyway, can also not be always clear in the observation, especially for statistic limitation, but also other contamination. And that the correlation with the gas structure really helps to recognize the hadronic emission. And when we will have CTA and ASTRI, we will have a much better angular resolution with the large field of view instruments. So we will be able to see also structures which could be interesting to disentangle between gas structure or different type of interaction. Again, also from the diffuse components, we can understand what are the cosmic rays in our galaxies, and especially in the hadronic component. We can put limit on the contributors of cosmic rays by observing the diffuse emission. And we are now in a place where we can actually say with some demonstration that hadronic acceleration is not only being recognized in supernova remnants, but also in other type of sources like stellar clusters, and for example, the very interesting case of the Cygnus X3, which I showed that may contribute, may accelerate protons to PV energies and beyond. And I stress finally the the ratio that we should study the details of acceleration to understand what are the dominant sources of cosmic rays. And to do that, before we have statistical significant data on sources from neutrinos, we can always rely on the synergies with the X-rays and radio emissions. So thanks a lot. I conclude here.
Thanks, Giada. So I think Reshmi left already. So I'll run the discussion part.
Yeah, she said that she had to leave at 4. That's why I wanted to rush, but I couldn't.
Yeah, but okay. Anyway, typically I am running the discussion, so typically Reshmi is leaving earlier. So, questions?
C'est moi.
Yeah, thank you very much for the nice overview. So the potential evidence that the cosmic ray electron to proton ratio might be depending on age is very interesting. But how does it correspond to the cosmic rays that are escaping the source? I believe, well, maybe this is not entirely established, but for protons, I believe many people think that the higher energy particles escape first upstream and then progressively the lower energies, cosmic rays. What about, is it similar for the electrons, or could the escape process be somewhat different for electrons, protons?
No, of course, is something that has to be taken into account, and it has in my presentation I was a bit fast because it was just, but the details needs to be taken into account. But yeah, the propagation is similar. The escape is similar in for electrons and protons, and is the same. The only thing is that electrons also lose energies. So when you do how do you say when you do a consistent model, you also have to account of that high energy electrons not only escape fast, but they also do lose energy faster than protons. But in general, the propagation is the same for electrons and protons. And this is why also there is an accumulation of electrons. There might be accumulation of electrons that are then released in a phase where it's well, sorry, no, this is nothing to do, but in general, yes, to your question, it has to be taken into account, and it is the same, the propagation of, in the escape of electrons and protons.
Okay, thank you.
Some other questions? I see there are 2 questions. Fabio?
Okay.
Yes, hello. Yeah, thank you, Giada, for the presentation. And about the same KP here, I was wondering how was the KP obtained in the table that you show? Usually, we do the SED modeling where we do inverse Compton and hadronic, but this is usually a one-zone model where we don't account for losses. And so if you were to do a time evolution model, then the electrons lose energy, and so maybe this number changes a bit. Okay, can you comment on that?
Yeah, of course, this has to be taken into account if when do a proper analysis. When you all these numbers, they are from different references, as I'm showing this again. So in every case, the single supernova has been studied in detail. From what I'm concerned here, so I'm also taking into account the effect that you are saying, so that electrons may lose energy faster. But this is important. So it's important to decide where to normalize this KAP. Indeed, I constructed this table because I was curious to see this comparison, but yes, it's true that it has to be consistent. You have to be sure to compare the values in an energy where the energy losses of electrons, they do not play a significant role, but this is always usually taken into account in the normalization. In some papers, I was a bit difficult to understand the normalization, so I left them out. But in general, if you see here, they are normalized at lower energies where they do not play a significant roles, the losses. So in general, the two spectra, the electron and the protons, they should be parallel. So they should have the same slope.
Okay, yeah, thank you.
Yes, may I, is absolutely. May I just add that if you are talking about low energy protons, which produce the pion bomb, at least, or more generally up to TeV or 100 of GeV particles, then protons of electrons are quite similar. Electrons cool through branch along a bit faster, but anyway, these are not very fast cooling, so protons, electrons are essentially very, very similar. Yeah, Matthew?
Thank you for the talk. So, we often discuss a lot about the maximum Lorentz factor for the acceleration of these systems, and obviously it's important to see what's going on with the contribution at the highest energies. I'm wondering what the constraints exist on the minimum Lorentz factor of the accelerated protons in the galactic systems, and whether or not there's anything, because often in blazars you can get these kind of narrow distributions of accelerated particles, and I'm wondering if it's always just very broad in terms of the minimum Lorentz factor, or whether we have any constraints on the minimum Lorentz factor that gets washed out somehow.
Any constraint on the minimum Lorentz factor of protons?
Yeah, so like when you're doing the broadband modeling, just gamma min and whatever's being happening.
Oh, well, here I don't put any limit on the low energy part, in the sense that this is, since the model accounts for, I just put the rest mass as a minimum energy. And so basically kinetic energy is 0, but it does not account too much, I would say. I'm not sure I get your.
I'm wondering about the particle distribution overall, not just the maximum, but the overall shape of the injected proton spectrum, whether or not it has a cutoff at low energies, or whether or not it doesn't, or whether or not we know that it has or doesn't have a cutoff at low energies.
Okay, here I don't put any cutoff, and the spectrum is a power law that that is fixed in shape by the Fermi data. It is actually a power law with a cutoff, you can see here, but the cutoff region has no data. So in general, in the paper, then we are commenting that the cutoff or the maximum energy will be only proven by higher energy instrument. At low energy, here you have above 200 MeV, you have the threshold of the pions, so you don't have any, the pions, the protons that are at lower energies, they simply do not contribute to the emission, because they have to.
Giada, I understand the question is just because in blazar modeling for electrons they use gamma 1, gamma 2, gamma minimum always.
Okay.
And so question is, do you have, okay, we have a cosmic rays. In galactic sources, no need for that. And because as long as diffusive shock acceleration, of course, this has a very broad distribution. In blazars, probably, I don't know how it's necessary to have a gamma mean, but there could be gamma mean. That is the different acceleration mechanism, maybe the reason. I understand the question is that in blazars, typically we have gamma mean. But if to add, I mean, we have also gamma mean in Parsavin nebulae. So in the Parsavin nebulae, there is a gamma mean. It's around 100 GeV, which is probably or 10 to 4, 10 to 6 Lorentz factor, which is probably the Lorentz factor of the pulsar wind. So typically you already have a very large Lorentz factor, and after termination you accelerate, but minimum keeps like that. So, but otherwise in protons, but formally you could have, I mean, Giada is showing like in the clumps, if not, it's not acceleration spectrum, it's propagation effect. Particles, high energy particles go very deep to the clumps, and low energy do not have time to. So you could have sometime this kind of distributions, but it's more propagation effect.
Yes, I was not, I was not thinking about that, but also would, I mean, let's say that if the data do not require, we do not put minimum energies, minimum Lorentz factors. We allow the spectrum to go to zero.
Maybe one related
So it's
question.
basically
Yeah. Oh, go ahead. Go ahead, Matthew, if you're.
Yep,
go ahead, please go on.
Yeah, I was just gonna say in blazars though, the estimate of KP depends critically on the gamma min for the electrons at least because the spectrum is steep. So the lower energy you go, the more you pile up. So how do you know you don't have a lot of like 100 MeV electrons or something like that? What assumptions do you make? Does your gamma min, if the spectrum is steep, S greater than 2, whatever, everything depends on gamma min or E min.
Oh yeah, but you are saying, well, but I normalized to I normalized to 10 GV, so
Okay.
I get the I'm quite far from that problematic energy range. And
Okay.
and as I was saying in my model, for example, here the protons and electrons have the same slope up to the maximum energy, which is different from both. And the minimum energy is not probed here. So also the low energy losses are not taken into account because we do not have data in that energy range.
Right. Thanks. Yeah, that makes sense. In blazars, the electrons can contribute rest mass and bulk energy to the jet, so it
but
matters.
there could be also, Paulo, there could be a
Yeah.
reconnection, which could
Yeah.
give some other type of
Yeah.
distribution. But for it's the same in pulsar nebulae for electrons.
Hmm.
Because if we originate from the pulsar wind, if pulsar wind originally has a Lorentz factor 10 to 4, 10 to 6, then, and we know there is a cutoff below 100 GeV in the Crab Nebula, should be the cutoff. So there is a gun, I mean.
Yeah.
But for protons, if the diffusive shock acceleration, you don't expect actually.
Yeah.
I don't know, I'm not expert in diffusive shock acceleration, but typically it's very broad. But propagation effects could give you one, just what Giada mentioned when you go to the dense environment. I mean, just the text. So low energy particle couldn't follow to highest energy particles. And then highest, at some point you could have a kind of cutoff, or if particle escape, the low energy GV protons can be captured in the shell, while high energy could go outside. So we could have some cutoff, very hard spectrum beyond the shell. So that's
Yeah.
If I may add also in this type of source, which is I always I didn't mention because for me now for me it's taken for granted, but the fact that we have the acceleration here, but also the gas distribution peaks here, so we don't really have a propagation effect here. So propagation effect here, so that may have some cutoff in the low energy part. They do not play a role because the gas is really close to the acceleration region, if that makes sense.
No, but Jade, if your cloud is far from accelerator, it could be just you'll see inside the cloud only very high energy particles, but not low energy. Depends on the time, diffusion coefficient,
Yeah, but
distance. So
this
could be
is what I was
situation.
saying that since so here propagation is not accounted also because the target is really close to the acceleration region. This is what I meant.
Emma.
Hi, Giada. Ciao.
Hi.
Very nice talk. I wanted to ask you something also related to W44. I think you showed it in I think it was slide number 30 something, where you had the potential for MEV detectors, and you had the Bremsstrahlung contribution. There, exactly here. So I had two questions there. What's the maximum energy you had to assume there in electrons? Is that, I assume this is also defined by cooling, how you cool the electrons, right? But for something like W44, is that compatible with the maximum energy you see? And are those electrons like confined in the supernova, or they are diffused in the inner part of the supernova?
Well, this is a simple modeling. Actually, I also wrote here that electron losses are neglected in this modeling, because this is just to say that the ideal potential of this type of investigation. But on this part, the emission here is the emission from the shell, so is what we see from the main remnant. And there is not real modeling here. It was just to try and find a Bremsstrahlung shape that could fit the data. There is no theory behind that, no real theory behind that. So this is just to say about the shape. If you want to be agnostic on the acceleration region, on the propagation and everything, we just say this is the shape that could fit the data. Here also they are not, you should also account for low energy losses due to ionization, but those I was checking for another reason. They are up to 100 MeV. Yeah, up to, so here they would shapen a bit the spectrum over here probably, but
Yeah, well, actually, I meant more like the right plot, not the left. The
the
low
right
one.
one. Here
Yeah, this one. Yes.
this is my thing. I didn't consider the losses, because here probably they will the electrons, they will cool at the lower energies, but here also there is no inverse Compton accounted, so it's really just a model to show the low energy part. The high energy was neglected.
Okay.
But it's nice that it fits. So it's
it is
but
nice.
I think it's fake.
Well, let's see.
Well, let's see. I mean, I don't know.
Thank you.
Yeah, you're welcome.
Giada, I have a question. You said about your communication with ChatGPT, but I didn't get. So, what did you ask? Which supernova remnants really contain the pi zero bomb?
Yes, I
And
see. For
then
how many gamma ray
ChatGPT answered
sources?
that, yeah.
I ask for how many gamma ray sources there has been clear detection of a pion bomb.
And the answer was also IC433.
Yes.
Is it true?
Well, in the Fermi paper is claimed in this way. You see, you have the detection of the shape, which is very similar to W44.
No, but
I'm
there is a strict definition when you could say could be also not pion bomb, and that is this Bremsstrahlung spectrum 1 over E gamma, right? So ECD goes like proportional to the energy. So if
Yeah,
something is harder than that, it goes sharper than that, then cannot be Bremsstrahlung, because Bremsstrahlung in the best case could produce 1 over E type differential spectrum. So that is the case was for W44. But
I
I
indeed.
see for free, I don't think this is the case. It's just a bit more not. We are
To be
saying it looks like a pi zero bomb.
Yeah. No, to be fair, I mean, we did this work together. We checked on this for W44, but we didn't do it with the IC433. I'm not as much expert on the IC433, but I think that historically from the Fermi collaboration, this is what they are claiming. But it's true that also here you have some Bremsstrahlung that may account for that.
No. Historically, there was also W28, actually the first one. So there's several candidates. But what I want to understand is really, and to my knowledge, so far was only W44, which gives such a sharper than SED proportion to energy.
Yeah.
That 100% kills Bremsstrahlung.
Yes.
Because best case you Bremsstrahlung, you could not get harder than 1 over E. So that is, and there are no other mechanisms. So I was a bit surprised but no, they all of like. I mean, you could not, for example, actually people think that is W428 also is just one of the best examples. They are good examples, but if you use this very strict definition, because I mean, E minus break a 2 GeV electron spectrum, as you said, is perfectly a reproduced bump.
Yeah, to be fair, I would maybe it's time to restudy this part. I am also not aware of all the broadband modeling of AC433. It appears it has some dense gas and some I've seen some presentation also on the X-ray part. So, I mean,
It's
yeah,
good to check. That is my question. Actually,
yeah,
good
yeah,
to
it's
through all these mechanisms, check is the case is easy, and then tell ChatGPT the right what is true.
yeah. I mean, it's always sometimes it's always disappointing me, ChatGPT, but this time it was proving my
No, it's
point.
not disappointing, but this, if
But
we ChatGPT learns from the literature, in the
yeah,
literature claims is clear pi zero bump, then ChatGPT is clear pi zero bump. If you write a paper, if you say there's only W44, then ChatGPT will say only W44.
yeah,
So
okay.
I think it's good to check.
Yeah,
Really,
yeah.
there are not many, in fact, and now Fermi has more data
No,
and then
indeed.
more
We have
statistics.
now more statistics because the paper from Fermi was 2013. So yeah, would be good. I mean,
It's
maybe
based on the 2014, this
yeah,
WSIC433. No, but
yes.
that is, and for pi zero bound statistic is a critical issue. It's
Mm.
very important for W
Well, now I'm
zero bound.
remembering that there has been some studies by the Fermi collaboration of the low energy part of supernova remnants, but I have to admit I didn't check them. I remember them at some conferences, so maybe the solution is already there. But now I'm
I
just
think
remembering.
Marianne Lemoine made a paper on the Fermi collaboration that was dedicated to search for low energy and
Mm.
revisit all sources in the catalog to look for Pion bump. Then, of course, it was more looking for curvature. And then, as Felix said, from something that is curved to it's clearly pi zero and not Bremsstrahlung, that's another step. But the paper was looking for curved sources in the low energy. And they were finding, of course, more than two. If you look at something that is curved, I don't remember the number, but it was half a dozen or something like that, that are curved, not necessarily meaning that it's a pion bump. But
Indeed, I remember the presentation by Marianne, but is the paper then out? Because I remember the presentation, but not the paper.
yeah, that's been several years back. So no, it's out.
Fabio, is very interesting to clarify this question. I mean, of course, there could be pi zero, but this was strictly pi zero because, I mean, this electron spectrum E minus like 1.6 break at 2 GeV, and then E minus 2.6, which comes from the interstellar medium, perfectly reproduces also the bump type structure. So that is good too. And another thing, just observationally, of course, if you have very flat spectrum, in SED, you don't see the bump. In fact, the bump you see at 1 GeV or high energy is 1/2 GeV. In SED, you don't see 70 MeV bump, and kinematic bump is about 70 MeV. So when we multiply E square, we absorb that. So basically, we have to fit not SEDs, but differential spectrum. So that is a bit more straightforward to do because this bump is really, and bump we expect at 70 MeV, in fact, not. And so what we see GV, it is just the result of this multiplying E square. And that actually, there you have even bump there. There you go to E-2 and then continue like E-2, even a bit harder. But it's very interesting question. I mean, now Fermi has so much data. I mean, it is good to return it to, and there are maybe 10 good candidates to check.
As you know, the problem for the low energy part, 100 MeV and below, is that you add more data, more photons, but then the problem is that you are limited by the systematics due to the galactic diffuse, and this is what is driving the errors and not anymore the statistics. I think with
No, we know about
yeah.
that, but still it's wise to, you have now new
Yeah,
tools. Then
But so more data doesn't help you in that here. You are still struggling with the systematic of the diffuse model. But probably if this was 2014 for 2013, for example, certainly there is much more data. So yeah, that will help. But then you have to play with those systematics of the diffuse.
No, I understand. There's saturation at some level. But if you take, I think from 2013, there's no saturation still. Another 5 years, maybe at the end you come to saturation.
There's been other papers since 2013.
Okay, so more questions?
That's a good question. So in terms of if you have Bremsstrahl electrons in your W44 plot, they're very high energy, so there's a huge synchrotron radiation, which is detectable in your, let's see, when you had, let's see which plot it was. You were modeling W44 and you had
You mean synchrotron in radio?
X-ray, hard X-ray?
But the X-ray is a different story. X-ray is just 100 TeV electrons.
Yeah.
And they don't.
There's another plot where you made that one. See there, you have synchrotron 10 microgauss. Is that?
Yeah, is yes.
That's detectable by NuStar already, maybe.
Okay, yes. But again, remember that I was not accounting for electrons energy losses. I was really
that is a bit
the maximum and so on.
It is a bit superficial. 100 TeV electrons do not survive 10 to 4 kilo years, 10 kilo years. So, and then acceleration stops at the first 1,000 years. So they should not be 100 TeV electrons, of course, if nothing new happens or there's a pulsar, but otherwise you don't expect.
Yeah, I mean, my bad that I did not. I just, since I was focused on this part, I neglected this, but I understand it raises a lot of questions.
Yeah.
But it's good comments.
Okay.
But a lot of people do that, Giada. I mean, this is interesting. They just continue to 100 TeV and they see an X-ray shell. And this X-ray shell for this all supernova rays is simply thermal shell. I mean, you don't expect X-ray shell for the old supernova remnants.
Indeed.
Okay.
I think here I just wanted to dream about something to be seen in this part of the spectrum. So I was pushing everything, but
no, but if you have it, it's a big discovery. I mean, if you have an X-ray non-thermal shell, it's absolute discovery, or there's no diffusion shock acceleration anymore. It should be something else.
Yeah.
That is actually wise to search for these kind of things, in fact. But keep in mind that in standard picture should not be.
Indeed.
So thanks, Giada, for a nice talk.
Yep.
Thanks everyone for listening and the discussion.
Yes, it was very good. And we will have next, in 2 weeks, complimentary talk on diffuse gamma rays by Fabio. Okay, thank you. Bye.
Great. Thanks, Giada. Okay. See you, Felix.
Bye-bye.